All right, we're back. We're on page 3 of Calc AB Notes 1, which is sort of a reintroduction to some of the calculus stuff that we did last year. So if you're new to my videos and you're looking to learn the very beginnings of calculus, you really need to go back to math analysis, notes 18 on till the end of the year. But there are videos of those also, if that's what you're looking for. So you might want to start there. Otherwise, let's get started on this. So given that f of x equals radical x, sketch a graph of f of x below. All right, so this is like not my favorite thing to do because it just highlights how bad I am at drawing. So like I know it goes through 0, 0, 1, 1, 4, 2, 9, 3. So I'm doing the perfect squares, obviously. This. And I gotta like somehow get a curve through this. It seems impossible. I wish this had like, see, I'm off. It's because I want it to grow too fast, I think. This, and then I gotta go. I don't know. I think that's pretty okay. I mean, it doesn't look great, but that's probably not the hardest problem that we're gonna do. Or maybe it will be. Find f prime of x using the limit definition of the derivative, confirm using the power rule. Okay, so limit definition tells me that f prime of x will be the limit as h approaches 0 of f of x plus h, so radical x plus h, minus f of x, which is radical x, all over h. So what technique do we use on this? Well, I see something that I can rationalize, so I'm going to rationalize it. I'm going to multiply by radical x plus h plus radical x over the same. So clever form of 1, very common technique in math to multiply by a clever form of 1. So when you do this, you want to expand the thing that you're doing it for, right? We're trying to rationalize the numerator, so we want to expand the numerator. We do not want to expand the denominator. It will be a waste of time. So in general here, when you multiply by the conjugate, you always end up with like a squared minus b squared. So the first thing squared minus the second thing squared. So in our numerator, we're going to get the quantity x plus h minus x. And in our denominator, so I see a lot of people, myself included, often forget the conjugate in the denominator. I do it all the time. But then when I try to evaluate, I'm like, this isn't really working out. And then I look and I'm like, oh, it's not working out for a reason. This. And then if we simplify this, so I'm gonna do like multiple steps at once here. You get x minus x in the top, which is good because everything that doesn't have an h should cancel here. And it did. So we get x minus x gone. We have h over h. I'm going to cancel those and just say that I have this x plus h plus radical x. Now if h is equal to 0, I get 1 over root x plus root x. So I get 1 over 2 root x. So I believe that that's f prime of x. Okay, so I'm gonna like write that. Therefore, f prime of x is 1 over 2 root x. Okay, so what about, that does not look great. My radicals, sometimes my radicals and my 5s and my s's sometimes look a little close to each other. So you want to watch out for that if you're me. All right, so we're supposed to confirm with the power rule. So I'll do it in another color. So if f of x is a square root of x, so radicals are the enemy of the power rule. So you basically need to convert this to rational exponents. We get this. So now power rule, f prime of x should be bring the exponent down and then subtract 1 from the exponent. So we get this. But then this you can rewrite as 1 over 2. So you could leave it as a rational exponent, but since we're trying to show that it's equal, I think we should make them look the same. So 1 over 2 root x. So we get the same answer either way, obviously, because you better. So the next question, write the equation of the tangent line to f of x at x equals 9. All right, if I'm going to write a tangent line, I need to know 2 things. I need to know the point, which means I need to know f of 9, which is just square root of 9, which is 3. There's really no reason to write that square root of 9 part. You could just write f of 9 as 3. Then I need f prime of 9, which is going to be 1 over 2 square root of 9, or 1/6. Again, you could just write f prime of 9 as 1/6. It'd be fine. So our tangent line, and you want to like say what it is. So our tangent line is y minus the y value equals the slope, and then x minus 9. So I always think problems like this where you have to add it to the graph really highlight why you want to be using point slope form. So we use point slope form, and what we're going to do is point slope form highlights the point of tangency. The point of tangency is 9, 3, right? So I'm going to go up here. I'm going to find 9, 3, like here. Different color, let's say. So it's like here. And then from there, I'm going to basically use the slope, right? So the slope is 1/6. So if I go up 1, I go over 6. And now you can see that I definitely did a bad job. And then if I go down 1, I have to go back 6. I did a better job on this end than I did on the other end. And then I want to put a line through these. So like, good luck to me. Okay. Here we go. Get very nervous drawing lines. Something like this. So there we go. Okay, so then you can see how bad a job I did of drawing the curve. How do you know that it's bad job? Well, the fact that this part, that should definitely be below the tangent line. So I know that I did a bad job because the tangent line is always above this. Like, just imagine I were trying to do like, you know, if I had this, if I didn't get all nervous because of all the boxes, right? It's the boxes, the lines, the vertical, the horizontal. Like now you feel compelled to like try to do something better than you're capable of. But if I hadn't had that, I would have had a picture that looked more like this, which would be more correct. So it turns out that more detail made it worse on me. I knew that was going to happen. So the tangent line should always be above the curve, which is important. We're probably going to talk about that. I don't really know. Oh yeah, here we go. Based on the shape of the curve, is this an over or underestimate? All right, so first let's approximate it. So f of 9.1 is the square root of 9.1. So this is one of the ways in which you will use tangent lines. We'll say f of 9.1 is approximately, so it's approximately the value you get when you plug into the tangent line. The tangent line right now is not exactly written in a way that we can easily plug into. So like you might, this is the only concession that I'm willing to make to point slope form. You should always be using point slope, but if you're going to approximate, it's very helpful to move like y0 or f of a over to the other side. So here we'll get 3 plus 1/6. And then the beauty of point slope is you use the tangent line only very, got Siri popping up here. You use the tangent line very close to the point of tangency. 9.1 is really close to 9. So when you plug it in, the -9 kind of knocks off the integer part, and you're just left with that little decimal. So here we have 3 plus 1/6 of 0.1, but I'm going to write 1/10. So that's 3. So I'm going to make it, what is it? 181 over 60. Which is like really close to 3, which is what I would expect, right? Because 9 is 3 squared, so 9.1 should be something really close to 3, but then squared. So this is our approximation. So notice a couple of things here. So the first, that's an approximation for sure. But then after that, we started using equal signs because those things are equal as you read from left to right. It's f of 9.1 is approximately all of these things, but these things are equal to each other. So that's why we use equal signs there. Let's go up and look at the picture. So in the real picture, it's hard to tell. 9.1 in the like fake picture, I'm going to use that one instead. 9.1 would be somewhere like here. And the value that the tangent line gives is up here. So you can see that because the tangent line is above the curve, the tangent line has given us an overestimate of the value. So we're going to say our approximation based on the shape of the curve, is this an over or underestimate? I'm going to say, so this is an overestimate. An overestimate. And we need to give a reason. So I'm going to say because. So I'm going to say two different things. So you might say because the tangent line is above the curve, and that's okay for now. A better answer and this, you really have to remember stuff though to know this one. A better answer, so let's kind of like fork off of this here. So because f of x is concave down. So I probably at that point though, because I don't trust people to know exactly what that means, I would probably say f of x is concave down. What does it mean for it to be concave down? There's a lot of things, but the easiest graphical way of thinking about it is that the tangent line is above the curve. So if f of x is concave down, the tangent line is above the curve. So I would probably say because f of x is concave down, which means the tangent line is above the curve. And so you're gonna go to an overestimate. But I still think trying to get concavity in there is a better idea than not getting concavity in there. So I'm gonna actually finish these. I was thinking about cutting this here. I don't know what I'm up to. I should run a timer when I'm like making the videos, but I never do. All right, write the equation of the line secant to f of x. So like that's weird. I think usually it just says find the secant line to f of x on the interval, but like I tried my best, I don't know. Write the equation of the line secant to f of x on the interval from 9 to 16. All right, so we're gonna need a slope. So I'm gonna do f of 16 minus f of 9 over 16 minus 9. But remember, f of x is the square root of x. So f of 16 is the square root of 16, which is 4, minus the square root of 9, which is 3, and then divided by 7, so that's 1/7. So this will be, I'm just gonna call it m. Well, you know what, let's do m and then a little subscript for secant. M sub sec, the secant slope. All right, now we have a choice, right? So I know that f of 9 is equal to 3. So I could write the secant line is y minus 3 equals the slope, which is 1/7, and then x. 1/7 is a weird answer. Yeah, no, that's right. X minus 9. That's a perfectly good answer. But we also know that, so with a tangent line, you don't really have this option because there's the point of tangency. And that's what you basically have to work on. Could be that the tangent line intersects the curve again. We just like typically do not know that. So here we have two different points we could potentially use. And you'll see, well, you would see, I'm not gonna do it. This would be y minus 4 is 1/7, and then x minus 16. So if we expanded these, it's really hard for me to believe that these would give me the same thing if I expanded these, but I think they would. So these, either of these, so how do I indicate that? Let's say both are good. So is one better than the other? Not particularly, although if you're gonna try to use the secant line to approximate the function, then like if this is the next question. So let me just, I'm gonna add the graph and then I'll come back and talk about that. All right, so at 3, no, what am I doing? 16, 9 and 16, okay. So 9 and then 16, this is an impossible task. I gotta get a line through there, great. Let's say that, and then I'm gonna actually like try to move it back a little. I don't know, this is my secant line. Okay, so another feature of this thing, and now you can see you go up 1 and over 7, so 1/7 is definitely the slope. Another feature of a curve that's concave down is that the secant line, so I'm gonna draw a random secant line, so it's not the same secant line, but you can see that this would be the same no matter what secant line we use for this concave down curve. The secant line is below the curve. This is a big deal because frequently you're asked questions like, use the tangent line to approximate something, now use the secant line, what's the deal? And sometimes you'll, like, tangent line is an overestimate, secant line is an underestimate. And so therefore the real value is somewhere in between the tangent approximation and the secant approximation. That's where we're kind of headed in life, right? So that's a thing. So for example, if we use the secant line, and I notice I didn't ask this, and maybe that's because maybe these notes could use a tune-up, who knows? If we had used the secant line to approximate f of 9.1, we'd get a number that's below the true value. And then we'd have a nice inequality that we could say like f of 9.1 is definitely in between the secant approximation and the tangent approximation. And that would have been a great question, but it is not the question that I asked you. So the question that I chose to ask for some reason, good grief, let me zoom out. Trying to scroll through zoomed in text is like, I think it's probably dizzying anyway. I never watched the video, so I don't really know. Use the secant line to approximate f of 13, which is the square root of 13. So I'm gonna say, so which secant line makes more sense? Which one is closer? So it's 4 away from 9 and it's 3 away from 16. I don't think it really makes much of a difference. I'm gonna use this one. So, but I don't think it makes a difference. Like you get the same number no matter what you use. It's just like sometimes it's a little, like if it was 15.9, then obviously you want to use the one that's based around 16. If it was 10 or 9.2 or 9.1, like it should have been, then it would make sense to use the secant line at 9, but like whatever, they're the same line, they're just different versions of it. So I'm gonna say f of 13 is approximately, that approximate really matters, be 4 plus 1/7 of 13 minus 16, which is like really far away from a calculus perspective. Like being 3 units away is like the Grand Canyon of calculus. 4 plus 1/7 times -3. So what are we doing here? 28ths? No, sevenths. 28 sevenths minus 3 sevenths is 25 sevenths. So again, the first one's an approximate sign. Everything after that is actually equal. And so I'm going to say, since f of x is concave down, you can actually abbreviate that as CD. The secant line is below the curve, which is a feature of being concave down. Below the curve. Curve? No, the curve. Therefore, this is an underestimate. So we underestimated it by using our secant line, which is fine. It's an approximation, and it's nice though to like know if it's an over or underestimate. So the last thing I want to do, you don't have to hang around for it, but I just want to like go to the calculator and like compare the values that I got. So I'm gonna try to start a new document. So for example, in the first one, we approximated the square root of 9.1. So square root of 9.1 is this according to the calculator. Our tangent line approximation was 181 over 60. Super close, right? And part of that is that 9.1 is very close to 9. If we were even closer to 9, like 9.05, the square root of 9.05, the tangent line would do an even better job. The closer you get to the point of tangency, the better the approximation. At the point of tangency, the function and the tangent line have exactly the same value. So that's kind of like an important thing that we're dealing with. And then the other thing, square root of 13. So this I think won't be anywhere near as good, but it should be an underestimate, right? And notice, I forgot to mention, this is an overestimate, right? Because it's higher than the actual value. Not by much. Like according to this, 0.000, 4 zeros and then a 5. Like that's to 3 decimal places, same exact answer. Here our secant line would be 25 over 7, which is like, it's lower, which we knew. It's not super great, which we also kind of knew because 3 is really far from 16. And also, I don't know if this is true. I think secant lines in general just do like a worse job, which kind of makes sense because they're not really, they don't share the same like the slope. They don't share that geometric property with the original curve. But anyway, that's this whole page. So I'm going to cut this here, and then I will come back. I do think it says at the bottom, a quick sketch is always useful in making sure that you're thinking correctly. Can't stress that enough. Draw pictures. Calculus it's very much like a visual form of math, and then like the algebra stuff, sure, it's a part of it, but like you got to have all these pictures in your head. And if you do, I think you'll be fine. So I'll see you in the next video when we will keep going with this stuff. So see you then.